Chemistry 30, Lesson 7, the common ion effect. To this point, we've discussed situations using water that does not contain ions, but our water often does contain dissolved particles. Pre-existing calcium ions in tap water would affect the amount of calcium-containing salt that could be dissolved. So when we make our calculations, we will have to take into account pre-existing ions if mentioned in the question. Example 1, how many micrograms of copper 1 chloride can be dissolved in 100 milliliters of deionized water? So we're looking for the number of micrograms of copper 1 chloride, and we know that we have a volume of 100 milliliters. Now, take note, this does not contain a common ion. The next example will, and we're going to do it without a common ion, then with a common ion, so we can see what difference it makes in the amount of solid we're able to dissolve. Now, in all these questions, we always write, to start off, the balanced decomp reaction of the potential solid. So CuCl becomes copper 1 ion and chloride ion. From this balanced decomp, we then make our KSP expression. Now, since we are not looking for KSP, we can take the KSP number directly off the green sheet. So right away, I can say that the copper ion concentration multiplied by the chloride ion concentration is equal to 1.9 times 10 to the negative 7. The number that came off of my green sheet. Now, what is the concentration of Cu plus and Cl minus? We don't know. We also don't know how much CuCl we're going to add, and that's what we're looking for. So we don't know how much CuCl we're going to add, but we do know that the concentration of CuCl that's added is going to equal, in the end, the concentration of the Cu plus and the concentration of the Cl minus. So we can substitute that into our KSP expression. The Cu plus concentration is X, the Cl minus concentration is X. From here, we can now solve for X. So X times X gives us X squared. We square root both sides. We now have a value of X. Now we're looking for the amount of CuCl, and we know that the CuCl concentration is equal to X because that's what we wrote in our balanced decomp reaction. That CuCl concentration equals X. So the molarity of copper 1 chloride is equal to 4.359 times 10 to the negative 4 molar. Now, molarity equals moles over liters. If I rearrange this formula, I wind up with moles equals molarity times liters. And I know the molarity, I just found it. I know the liters because it's in the question. 100 milliliters equals 0.1000 liters. So I multiply those two numbers together, and I know how many moles of CuCl can be added to 100 milliliters of deionized water. Now I simply just take that given, convert it to grams, and since it asked me for micrograms, well, micrograms is a smaller unit, and I've said before, all conversions are BS, so if one gets bigger, the other gets smaller. So if the unit gets bigger, the number gets smaller. The unit gets smaller, the number gets bigger. So micro moves the decimal 6 spots. Micrograms are small, so our number has to get bigger. We move the decimal over 6 spots. We wind up with 4,300 micrograms of copper 1 chloride. Example 2. How many micrograms of copper chloride can be dissolved in 100 milliliters of water that already contains 0.0011 molar barium chloride? Part B asks us, what is the concentration of all ions in solution? Now this is an example with a common ion. Before we start to add Cu plus and Cl minus ions, some of the chloride ions were already present. They will have to be taken into account when we do our calculations. So before we begin, we had BaCl2, barium chloride, already in solution. And we're told that the concentration of the barium chloride is 0.0011. Which means before we started, there was a barium ion concentration of 0.0011. And before we added any copper 1 chloride, there was already a concentration of 0.0022 molar chloride ions floating in solution. So let's do what we did last time, make our balanced decomp reaction. And we make our KSP expression from that balanced decomp. We can take the number from the green sheet, for the maximum dissolvable amount of copper 1 chloride is 1.9 times 10 to the negative 7. We are again going to add X amount, some amount of copper 1 chloride. The copper ion concentration will be equal to the same amount. The chloride ion concentration will be equal to the same amount that we added, but we have to also take into account there was pre-existing chloride. So in the end, the chloride concentration will be the X amount that we add plus the 0.0022 molar that was already present. So we'll substitute that now into our KSP expression. Cu plus concentration is X, chloride concentration is X plus 0.0022. I'm going to distribute the X into the brackets on the right-hand side, and that gives me then X squared plus 0.0022X. Now if I move everything over to one side, I wind up with an X squared term, an X term, and a non-X term, which means to solve for X, I'm going to the quadratic equation. So I substitute all my numbers into the quadratic equation. Now note, with the plus or minus, I have just put a plus sign in. And that's because, and for some reason, I'm not exactly sure why this is, but the sign with the plus minus always winds up taking the opposite of whatever the front term has. So after we substituted in the b value, we have a negative term to start off, so our plus minus is then positive. If when we substituted in the b term at the front was positive, we would then take the negative of the plus minus. Now before you punch this into your calculator, I want you to write it out exactly as is, but then we're going to add in 3 sets of brackets so we can put it into our calculator all in one step. So we're going to add in 3 sets of brackets. The first set of bracket is going to go around everything underneath the square root sign so that we take the square root of everything that's supposed to be under the square root sign. I also want to add another set of brackets around the entire numerator. If we don't do that, then it's going to do the division first and then add that front term afterwards. And that is not going to work out well for us at all. And the last thing is, and in this question it really doesn't matter, but in future questions it may, we always want to double bracket the denominator as well. Now if you punch this into your calculator exactly as it is now written, you will get X equal to 8.322 times 10 to the negative 5 molar. And we're going to finish this question off just like we did the previous question. We wanted to know how much CuCl. Well, we said CuCl is equal to X. We know that molarity equals moles over liters, so the moles of CuCl will be molarity times liters. So molarity multiplied by the liters given to us in the question, we wind up with 8.322 times 10 to the negative 6 moles of copper 1 chloride, which we will then convert to grams. And after we have it in grams, we will then convert that into micrograms by moving the decimal 6 spots to the right. And with that pre-existing ion, we were allowed to only add this time 820 micrograms of copper 1 chloride. So what are the concentrations of all the ions in solution? Just going to make a little room here. Now, if I look at Cu+, well, we said the Cu+ concentration is equal to X. So I just substitute that in. Copper ion concentration is equal to X. Other ions that we have, well, we have chloride ion, which is equal to X plus 0.0022. So X plus 0.0022 equals 0.0023 molar. Now keep in mind we are adding, so to keep track of significant figures, I'm going to have to take that X value out of scientific notation. And I'm going to have to stack them so I can figure out exactly where that round off line went. And when I run that round off line down, I see that I'm dropping the 8, which then pushes the 2 up to a 3. And that's how I got 0.0023 molar as the concentration of chloride ions. And of course, there was also that barium that was pre-existing that we did not add to. It did not change. So barium ion concentration is still equal to 0.0011 molar. And that's the end of the lesson. You're going to work on the SE7 assignment. But before you go, Did you know, because you're working with the quadratic, that it was actually invented by a Canadian? True story. Just think of the formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Get it? Get it? Yeah, okay. All right, well. All right, work on your assignment.